If the Sun were replaced by a black hole of identical mass, the planets would maintain their current paths. From a distance, a black hole behaves gravitationally exactly like a normal star. For decades, physicists struggled to accept their existence. In 1939, Albert Einstein published a paper attempting to prove these objects were merely a mathematical glitch in his own theory of general relativity. The math proved correct. When a massive star exhausts its nuclear fuel, the internal pressure vanishes and gravity triggers a supernova, forcing the core to collapse irreversibly. Our universe is teeming with these reality-bending objects. To understand the physics governing them, we have to travel toward the edge and look inside. The environment immediately surrounding a black hole is shockingly bright, producing some of the most intense radiation in the universe. This schematic maps the accretion disk. Gas spirals inward at near light speed, generating friction to heat the plasma to millions of degrees. Magnetic fields catch a fraction of this material, blasting it away in relativistic jets spanning thousands of light years. Closer in, the disk hits the innermost stable circular orbit. Past this line, matter is forced into spiraling inward. Just past that drop-off lies the photon sphere. Gravity is so intense here that photons of light are bent into a continuous orbit, circling the black hole like planets. Spinning black holes also create an ergosphere. The rotation physically drags the fabric of spacetime into a vortex, making it impossible for any object to remain still. These chaotic, glowing boundary layers surround the true, invisible gravitational trap that lies just ahead. That trap is the event horizon. This is the ultimate boundary where escape velocity exceeds light speed, ensuring nothing reaches the outside universe. From a distance, an observer would watch your image slow down and freeze at the horizon. Because of gravitational time dilation, you would appear to fade to a deep red and vanish before ever appearing to cross. To the person falling, the passage of time feels normal. You would cross the event horizon without feeling a physical jolt or noticing a change in the passage of your own seconds. Deeper inside, you would hit the Cauchy horizon. At this inner boundary, infalling radiation and matter build up into lethal gravitational shock waves and tidal forces. At the very center lies the Singularity. All the mass of the original star ends up in a microscopic point of infinite density, where matter stretches violently and our known physical laws break down. Reaching the Singularity represents the edge of human knowledge. It is the point where the foundational rules of our universe cease to function. Zooming out, we see these are dynamic entities. Black holes grow and evolve by violently merging with one another and absorbing nearby matter. These massive collisions send powerful ripples, called gravitational waves, through the fabric of spacetime. We detect them using laser beams inside vacuum tunnels that are several kilometers long. Using advanced infrared optics, we have discovered that early supermassive black holes acted as cosmic regulators, interacting with their host galaxies to dictate early star formation. Rather than being mere cosmic vacuums, black holes are fundamental engines that actively shaped the structure of the entire universe. They are not eternally permanent. In 1974, Stephen Hawking demonstrated that black holes can actually leak mass into the surrounding universe. Because of quantum effects at the edge, black holes emit Hawking radiation. This causes them to slowly evaporate over trillions of years. Fading into nothingness creates an unresolved paradox. We do not yet know what happens to the physical information about the matter the black hole consumed. The very object Einstein deemed an impossible mathematical error is now the primary key to uniting gravity with the quantum world.